Hello everybody. In our previous videos, we discussed about saturated hydrocarbons, right? Today in this video, we'll be discussing about unsaturated hydrocarbons. So first, let us discuss about alkenes. Now we know that alkenes are unsaturated hydrocarbons, right? And they have at least one carbon-carbon double bond. Fine? And the general formula of these alkenes are given by CnH2n. In case of alkanes, it was CnH2n plus 2, right? In case of alkenes, it's CnH2n. Fine. So talking about the structure of this double bond, what happens is alkenes contain one strong sigma bond which is due to the head-on overlapping of sp2 hybrid orbitals. Fine. And they contain one weak pi bond which is obtained by the sideways or lateral overlapping of 2p orbitals. There are two carbon atoms, right? There are 2p orbitals. So this double bond is obtained by sideways or lateral overlapping of 2p orbitals of these two carbon atoms. Fine. And also this double bond is shorter than that of the single bond, that is carbon-carbon single bond. And since this is a weak pi bond, that is the overlapping is weak. Fine. So because it is a weak pi bond, this double bond, that is alkanes, are ready to lose electrons. So what happens is they are attacked by the reagents which are in search of electrons. For example, electrophilic reagents, they need electrons, right? So these electrophilic reagents attack alkanes because they are in search of electrons. And thus, because of the weak pi bond, these alkenes are less stable than alkanes. Fine. So now, moving ahead, let us discuss about the preparation of alkenes. So the first method is the preparation of alkenes from alkynes. Alkynes have a triple bond between two carbon atoms, right? So in this method, when alkynes undergo partial reduction with dihydrogen in the presence of something known as Lindlar's catalyst. Now what is Lindlar's catalyst? Lindlar's catalyst consists of palladized charcoal. Palladized means palladium, right? So it consists of palladized charcoal which is deactivated with the use of some poisons like sulfur compounds or quinoli. Fine. So when alkynes undergo partial reduction in the presence of dihydrogen and Lindlar's catalyst, they give alkenes, and these alkenes thus obtained are cis alkenes. So when we talk about geometrical isomers, there are cis isomers and trans isomers. Fine. So what are cis isomers? Cis isomers are nothing but the compounds wherein the identical two atoms are on the same side of the double bond. If this is the double bond, the identical atoms are on the same side of the double bond. But when we talk about the trans isomer, what happens is identical atoms are on the opposite sides of double bond. So if this is the double bond, the identical atom, one will be here and one will be here. So they are on the opposite sides of double bond, right? So those are trans isomers. Fine. So in case of Lindlar's catalyst, we get cis isomers. But when these alkynes undergo reduction in the presence of dihydrogen itself, when alkynes undergo reduction with dihydrogen in the presence of sodium metal and liquid ammonia, we get trans alkenes. Fine. This is about the preparation of alkenes from alkynes. So the next method is the preparation of alkenes from alkyl halides. Alkyl halides means RX group, right? R represents alkyl group and X is nothing but halogens, right? So how do you prepare this from alkyl halides? So alkyl halides on heating with alcoholic potash. What is alcoholic potash? It's nothing but potassium hydroxide, KOH, dissolved in alcohol, say ethanol or something like that. So what happens when alkyl halides are heated with alcoholic potash? It eliminates one molecule of halogen acid. What is halogen acid? HX. Fine. So this is also called as dehydrohalogenation. Dehydrohalogenation, that is hydro is H and then halogenation is X, right? So it's removing a molecule of hydrogen acid, and it is also called as beta elimination reaction. So let me tell you. So we have this compound, right? The carbon to which the halogen is attached to is called the alpha carbon. Fine. and the carbon attached to this alpha carbon is called the beta carbon. Fine. So if there are two carbons, halogen is attached to this carbon, this will be the alpha carbon, and this carbon is attached to this carbon, right? So we call it beta carbon. After alpha comes beta, right? So it's beta carbon. So it's called beta elimination reaction because what happens in this reaction is halogen is eliminated from the alpha carbon, fine, and one hydrogen gets eliminated from the beta carbon. So it's called beta elimination reaction. And the next one is the preparation of alkenes from vicinal dihalides. What are vicinal dihalides? Fine, dihalides means two halides, right? Two halogen atoms, right? So dihalides containing two halogen atoms wherein the halogens are attached to the adjacent carbon atoms. That is two carbon atoms which are attached to each other and they have two halogen atoms. That is they have one halogen atom each. Fine. So these are called dihalides. Two halogen atoms attached to the carbon which are adjacent to each other. Fine. So when these vicinal dihalides are treated with zinc metal, it eliminates ZnX2. So this is also known as dehalogenation reaction. Fine. Next method is the preparation of alkenes from alcohols by acidic dehydration. So what happens is when alcohols are heated with concentrated sulfuric acid, we obtain alkenes by the elimination of one molecule of water. So now one molecule of water is eliminated from alcohol molecule in the presence of acid and hence is called acidic dehydration of alcohol. Fine. And this is an example of beta elimination as well. So what happens is one OH group attached to the carbon. Fine. The is called the alpha. It's attached to the alpha carbon. Fine. So this takes away an hydrogen attached to the beta carbon. So what happens is the OH molecule attached to the carbon atom takes away an hydrogen from the beta carbon and hence there is a beta elimination in this case also. Fine. So this is all about the preparation of alkenes from different ways. Now let us talk about the physical properties of alkenes. Fine. Similarly, like alkenes also follow the same trend, but there is a difference in the isomerization and there is a difference in the polar nature. Fine. Other than that, it's the same trend. And similarly, for the first three members of alkenes are all gases, and then the 4 to 14 members are all liquids, and the higher alkenes are all solids. Fine. And alkenes are all colorless and odorless, except for ethene. Ethene is a colorless gas. It has some faint odor. Fine. And all alkenes, they're all insoluble in water and they're soluble in non-polar solvents like benzene and petroleum ether, etc. So like alkanes, even alkenes have higher boiling point for the straight chain alkenes other than the branch chain alkenes. That is, the straight chain alkenes have higher boiling point as compared to the branch chains. Fine. So this is all about the physical properties of alkenes. Now we'll discuss about the chemical properties of alkenes. We know that there's a double bond between alkenes, right? And the pi bond is formed. It's a very weak pi bond and it's formed due to the sideways overlap, right? And since it is a weak pi bond, the electrons are loosely held by this bond and hence it can be easily attacked by electrophilic reagents, right? So let us discuss all these chemical properties. Fine. The first one is the addition of dihydrogen. We discussed this when we were talking about the preparation of alkanes, right? So when alkenes on reduction with dihydrogen in the presence of catalysts like nickel, palladium or platinum, they yield alkanes. Fine. This is about the addition of dihydrogen to alkenes. The second one is addition of halogens. So when halogens are added to alkenes, it forms vicinal dihalides. We just discussed about vicinal dihalides, right? And this is one of the examples for electrophilic addition reaction. Fine. The next one is the addition of hydrogen halides. What are hydrogen halides? Hydrogen is H, halides are X, right? So hydrogen halides are HBr, HCl, HI, like that. Fine. So in this case, the reaction of HI will be more than HBr and that is the rate of reaction. Fine. And which is more than HCl. Fine. When alkenes react with hydrogen halides, they yield alkyl halides. Fine. So this is also an example for electrophilic addition reaction. And now we'll see about the mechanism of this reaction. When we talk about the addition of hydrogen halides to alkenes, there are two different ways, and it's totally dependent upon symmetrical alkenes and unsymmetrical alkenes. Fine. So symmetrical alkenes, there's a symmetry in the molecule, and the addition of hydrogen halides is very easy. Fine. So when we talk about unsymmetrical alkenes, there are two different ways. Fine. With the double bond is the molecule is unsymmetrical, so the hydrogen halide can get added to either sides of the double bond, right? So both the carbon atoms can get. So this is decided by one factor, and this was given by Markovnikov, and hence it's called Markovnikov's rule. So what happens is, during the addition, it gets added to that carbon which possesses less number of hydrogen atoms. Fine. So the double bond is shared by two carbon atoms, right? So out of these two carbon atoms, the addition happens to that carbon atom whichever has less number of hydrogen atoms. So this is how the reaction proceeds. Fine. Now we'll discuss about the addition of sulfuric acid to alkenes. So when cold sulfuric acid is added to alkenes, we get alkyl hydrogen sulfide. And this is in accordance with the Markovnikov's rule. Fine. Next is the addition of water to alkenes. So when water is added to alkenes in the presence of traces of sulfuric acid, we get alcohols. Next is the oxidation of alkenes. So when we talk about oxidation, consider cold dilute aqueous potassium permanganate, that is KMnO4. That is called Bayes reagent. That is the cold dilute aqueous potassium permanganate, known as Bayes reagent. When it reacts with alkenes, we get vicinal glycols. And this is a very important reaction because in this process, the potassium permanganate gets decolorized, and this is used as a test for unsaturation. Fine. The next one is the ozonolysis. When ozone molecules, that is O3, fine, when it reacts with alkenes, we get ozonides, and these ozonides on further reactions with zinc and H2O give small molecules, organic molecules of aldehyde. And this is also an important reaction because it is used to detect the position of double bond in the molecule. Fine. Next is the polymerization. So when we talk about polymerization, we know plastics and all, right? Polythene. What is polythene? Poly is polyethene, right? Poly means large number. It simply means there's large number of ethene molecules in it. So when ethene molecules react at high temperature and pressure, they form polythene. And this the polythene is called polymer. Fine. And this process is known as polymerization. And since ethene molecules are adding up in a large number, each of these ethene molecules are called monomers. This is all about alkenes. Now let us discuss about alkynes. Alkynes means they have at least one triple bond between two carbon atoms. Fine. And the general formula is CnH2n minus 2. So in case of alkanes, it was CnH2n plus 2. In case of alkenes, it was CnH2n. And in case of alkynes, it's CnH2n minus 2. Fine. Moving ahead, let us discuss about the structure of this triple bond. Similar to double bond, that is alkenes, what they have is, they have one head-on overlapping of sp hybrid orbitals. That is sigma overlap. Fine. So one C to C sigma overlap of sp hybrid orbitals. And even the CH bonds are also sigma bonds. Fine. And there are two weak pi bonds, that is two lateral or sideways overlap of the two 2p orbitals of carbons. So now these pi bonds, these pi bonds are similar to that of the, like how we discussed in case of alkenes, right? They are weak bonds. Fine. And when we talk about the triple bonds, C triple bond C is stronger than that of C double bond C, which is stronger than that of C single bond C. And we talk about the bond lengths, C triple bond C is shorter than that of the double bond and single bonds. Fine. Now let us discuss about the methods of preparation of alkynes. Fine. First method is from calcium carbide. So first we'll discuss how this calcium carbide is prepared, and then we'll see how to get alkynes from calcium carbide. Fine. So preparation of calcium carbide is from two steps. The first step is you take limestone, that is calcium carbonate, CaCO3. On heating this limestone, we get quicklime, that is CaO. So when we take the CaO and react it with coke, we get calcium carbide, that is CaC2. Fine. And this calcium carbide, when it reacts with water, we get alkynes. Fine. The next is the preparation of alkynes from vicinal dihalides. We discussed about the preparation of alkenes from vicinal dihalides, right? It was dehydrohalogenation. So what we did was, we took vicinal dihalides and reacted it with alcoholic potash, that is alcoholic potassium hydroxide, and we got alkenes, right? So these alkenes, when they are further treated with sodamide, sodamide is nothing but sodium and amide, right? Na plus NH2 minus, we get alkynes. Fine. This is about the preparation of alkynes. So now let us discuss about the physical properties of alkynes. Fine. Similarly, like alkanes and alkenes, alkynes also follow the same trend. That is, the first three group members, the first three members of alkynes are gases, and then from the 4 to 8 members are all liquids, and the higher alkynes are solids. Fine. And all alkynes are colorless and they're odorless as well, except for ethane. It has some particular odor. And all alkynes are weakly polar in nature. Fine. And they're lighter than water, and they're also immiscible in water, like alkenes and alkenes. Fine. And now they're soluble in organic solvents like ether, carbon tetrachloride, and benzene, etc. Fine. And as the molar mass of the alkynes increases, the boiling point increases, the melting point also increases, and the density also increases. So this is all about the physical properties of alkynes. So now let us discuss about the chemical properties of alkynes. Alkynes are acidic in nature, they undergo addition reactions, and they undergo polymerization reaction as well. We'll discuss about all of these in details one by one. Fine. First, let us discuss about the acidic nature of alkynes. We know that sodium and NaNH2, that is sodamide, these two are strong bases, right? And they react with alkynes and form sodium acetylide. And this is very interesting because these do not react with alkanes or alkenes. So alkanes and alkenes do not react with sodium or sodamide, these strong bases like this. Only alkynes are reacting with them. What is making alkynes react with this? What is the reason behind this? So when this answer can be given by the sp character of alkynes. We know that the hydrogens in alkynes are attached to C triple bond C, right? That is the sp hybridized carbon atoms, right? So since it is sp hybrid orbitals, sp is nothing but s character is 50% and p character is 50%. So because of more s character, there is high electronegativity, and hence the hydrogens can be liberated very easily. Fine. And further, this hydrogen is directly attached to the sp hybridized carbon, that is C triple bond C carbons, right? And hence this hydrogen is acidic in nature. Fine. So when we talk about the acidic strength, alkynes have higher acidic strength than alkenes, which have higher acidic strength than alkanes. Fine. This is about the acidic nature of alkynes. So now we'll discuss about the addition reactions. Fine. So this C triple bond C, right? It adds up with two molecules of dihydrogen, halogens or hydrogen halides and undergoes some reactions. Fine. In case of symmetrical alkynes, it's very simple, right? A carbocation is formed and the reaction takes place. But in case of unsymmetrical alkynes, Markovnikov's rule is followed. We discussed about Markovnikov's rule, right? Alpha carbon, beta carbon, etc. So that is followed in case of unsymmetrical alkynes. Fine. So first, the addition of dihydrogen. This we have discussed a lot of times now. So addition of dihydrogen with alkanes, that is alkanes on reduction with dihydrogen in the presence of catalysts like potassium, palladium, nickel catalysts form alkenes, and further alkenes form alkanes, right? So this is about the alkynes reduction in presence of dihydrogen. Next, alkynes with hydrogen halides, that is HX, right? When they react with two molecules of HX, they give geminal halides. Until now, we discussed about vicinal halides, right? What is geminal halides? Find out about it. It's very simple. It just takes a minute. See what's the difference between vicinal halides and geminal halides. Fine. Next is the reaction with water. Like alkanes and alkenes, even alkynes are immiscible in water. So for the reaction of alkynes with water, we need some aid, right? So what happens is we take mercuric sulfate and dilute sulfuric acid and then react with in the presence of mercuric sulfate and dilute sulfuric acid, we react alkynes with water and we get carbonyl compounds. Carbonyl compounds are nothing but C double bond, right? Like aldehydes and ketones. Fine. Next comes the polymerization. Like alkenes, even alkynes undergo polymerization. And the linear polymerization is just simple. The polymerization of the monomers forming a linear chain. Fine. It's a simple one and it has many uses. Like it is used for electricity. Fine. It conducts electricity and it's used as batteries. It is used as electrodes in batteries. Fine. And when it also has cyclic polymerization. So this is a very interesting one. What is cyclic polymerization? When you take like 3 molecules of ethene. Ethene is nothing but C triple bond C, right? All these 3 molecules of ethene, when the ethene is passed through red hot iron tube at very high temperature, like around 600 degrees centigrade, that is 873 Kelvin, they form a cyclic compound of benzene. Now this benzene is very important in organic chemistry. Benzene is where the aromatic compounds start, right? Benzene is used for the benzene derivatives like drugs, dyes, etc. It has vast usage and vast applications. So this is the transition from aliphatic compounds to aromatic compounds. Now we'll be studying about the aromatic compounds. Now we'll discuss about the aromatic hydrocarbons. So we just discussed how benzene is formed, right? Benzene is a parent aromatic hydrocarbon. Fine. So benzene has the formula C6H6. That is, it has 6 carbon atoms and 6 hydrogen atoms. And there is a high degree of unsaturation. So the structure of benzene was given by Kekulé in 1865. What he said was, the structure of benzene is a cyclic arrangement of 6 carbon atoms in a closed cyclic arrangement, fine, 6 carbon atoms having alternate double and single bonds, and each carbon atom is attached to 1 hydrogen each, fine. And then this structure of benzene is a hybrid of 2 resonating structure, and usually hybrid is represented by, in case of benzene, it is shown by dotted or a circle inside the hexagon, fine. So, all the 6 carbon atoms of benzene are all sp2 hybridized. Fine. So, 2 sp2 hybrid orbitals of 1 carbon overlaps with the 2 sp2 hybrid orbitals of the adjacent carbon atom. So, between 2 adjacent carbon atoms, there is an overlap of the 2 sp2 hybrid orbitals and they form 6 C2C sigma bonds. Fine. So, these delocalized pi electrons of the carbon atoms are strongly held by the nuclei of the carbon than the localized electron clouds between 2 carbon atoms. Are you getting it? So the delocalized pi electron cloud are more strongly held by the carbon nuclei than the electron cloud between the 2 carbon atoms. And benzene, being a parent aromatic compound, to classify whether a given compound is aromatic or not, there are a set of rules. And this is called Huckel's rule. Okay. The first criteria is it should have planarity. So the compound should be planar. Fine. And the second criteria is there should be complete delocalization of pi electrons inside the ring. Fine. And the third criteria is it should have a presence of 4n plus 2 pi electrons. Here n can take values from 0, 1, 2, 3, etc. Fine. So what he said was, first one is it should be a planar compound. That is, it should have planarity. Second one is that there should be complete delocalization of pi electrons inside the ring. And the third one is that it should have a presence of 4n plus 2 pi electrons, where n is equal to 0, 1, 2, 3, etc. And these sets of rules are called Huckel's rule, and these are the set of rules you use to check whether a given compound is aromatic or not. Fine. So now let us discuss about the different ways of preparation of benzene. Fine. The first method we already discussed when we were discussing about alkynes, right? That is the chemical properties of alkynes. So benzene is obtained by cyclic polymerization of ethyne. So when you take 3 ethyne molecules, basically what happens is when ethyne molecules are passed over red hot iron tube at very high temperature around 873 Kelvin, we obtain benzene, right? The second one is decarboxylation of aromatic acids. So when you take sodium salt of benzoic acid, sodium salt of acid is COONA. So COONA attached to benzene is the sodium salt of benzoic acid. And when you react it with soda lime, what is soda lime again? NaOH and CaO, right? Sodium hydroxide and calcium oxide. So when you heat sodium salt of benzoic acid with soda lime, you get benzene. Fine. The third method is the preparation of benzene from phenol. So by the reduction of phenol. So what you do is when you pass the vapors of phenol over heated zinc dust, you obtain benzene. Fine. So there are three methods of preparation of benzene. One is the cyclic polymerization of ethyne. The second one is decarboxylation of aromatic acid. And the third one is the reduction of phenol over the heated zinc dust. So next let us discuss about the physical properties of aromatic hydrocarbons. Fine. So all aromatic hydrocarbons are non-polar in nature. And further, they're colorless liquids or solids, but they have characteristic aroma. Aromatic, the name itself suggests they have aroma, right? Every aromatic hydrocarbon has a characteristic aroma, but they're colorless, either liquid or solids. For example, you consider naphthalene balls. You have it in your houses, right? It's kept to preserve the clothes from, it's a moth repellent, or it's used in toilets, right? It has a characteristic aroma, fine? And these aromatic hydrocarbons are immiscible in water, but they are soluble in organic solvent. Let us discuss about the chemical properties of benzene, fine? So benzene undergoes electrophilic substitution reaction, and to some extent it undergoes addition reactions and oxidation reactions as well. So first we'll discuss about the electrophilic substitution reactions, fine? So there are various electrophilic substitutions undergone by benzene, like nitration, halogenation, sulfonation, Friedel-Crafts alkylation, or Friedel-Crafts acylation. So we'll discuss about all of it in one by one, fine? First one is the nitration. When benzene is heated with concentrated nitric acid and concentrated sulfuric acid, we get nitrobenzene. Fine. So for nitration, the reagents are concentrated sulfuric acid and concentrated nitric acid. Fine. Next, halogenation. When benzene is treated with a molecule of halogen like Cl2, Br2. Fine. When it's treated with a molecule of halogen in the presence of a Lewis acid like anhydrous AlCl3, FeCl3 or FeBr3, we get the halobenzene like chlorobenzene, bromobenzene, etc. Fine. So for halogenation, the reagents are molecule of halogen plus a Lewis acid like anhydrous AlCl3, FeCl3, etc. Next is the sulfonation. Sulfonation is got when a hydrogen of benzene is replaced by the sulfonic acid group. So in case of sulfonation, what we do is benzene is heated in the presence of fuming sulfuric acid, and then we get the sulfonic acid of benzene. Fine. So what happens is one of the hydrogen of benzene is replaced by sulfonic acid groups. Fine. That is SO3H. Fine. So next is the Friedel-Crafts alkylation. So what happens in Friedel-Crafts alkylation is benzene reacts with an alkyl halide in the presence of a Lewis acid like anhydrous AlCl3. Fine. So we get the alkylated benzene. For example, CH3 attached to benzene. That is nothing but toluene. Fine. This is about the Friedel-Crafts alkylation. For that we need alkyl halide and the Lewis acid. Fine. Next is the Friedel-Crafts acylation. So Friedel-Crafts acylation takes place when benzene reacts with acyl halide or acid anhydride in the presence of, again, the same thing, that is anhydrous AlCl3, that is Lewis acid. So what happens? Benzene reacts with acyl halide or acid anhydride to get acyl benzene. So these are all the electrophilic substitutions of benzene. Also, when the electrophilic reagent is in excess, for example, if chlorine is in excess, what happens is all the hydrogens of the benzenes are replaced by the electrophile. So when chlorine is in excess, all the hydrogens of the benzene are replaced by chlorine. Fine. This is all about the electrophilic substitution reactions. And these electrophilic substitution reactions takes place in 3 steps. That is, the mechanism for electrophilic substitution reaction is through 3 steps. Fine. The first step is the generation of electrophile. Fine. The second step is the formation of carbocation intermediate. Fine. And the third step is the removal of proton from the carbocation intermediate. So this is all about electrophilic substitution reactions of benzene. And then there is something known as ortho-para-directing groups and meta-directing groups. So there are two different ways where the incoming groups are directed towards the either ortho or para position or meta position. So the ortho-para-directing groups are nothing but the groups which direct the incoming groups towards the ortho and para position. Fine. And the meta-directing groups are groups which direct the incoming groups towards the meta position. Examples of ortho-para-directing groups are minus O, that is OH, that is nothing but phenol, OH, NH2, CH3, C2H5. So when all these groups are present with benzene, when benzene has CH2 group, OH that is phenol, or NH2 groups, all this what they do is they direct the incoming groups towards the ortho or para position. Fine. So meta directing groups include NO2, CN, CHO, COR, etc. So what all these do is when a benzene ring has NO2, it directs the incoming groups towards the meta position. So this is about the ortho-para-directing group and meta-directing group. So next is the addition reactions. So until now we discussed about the electrophilic substitution reactions, right? Now we'll discuss about the addition reactions. There are two major addition reactions. The first one is benzene under vigorous condition, that is high temperature and pressure, in the presence of nickel catalyst undergo hydrogenation and form cyclohexane. So benzene becomes cyclohexane under high temperature and pressure in the presence of nickel catalyst. Fine. So the next one is when three molecules of chlorine reacts with benzene under the UV light, it forms benzene hexachloride. Hexachloride is 6 chloride. So all the 6 hydrogens will be replaced by chlorine. Fine. This is about the addition reactions of benzene. Now talking about the combustion. So in case of combustion, when benzene is heated in air, it burns with a sooty flame and produces carbon dioxide and water. So talking about the combustion of benzene, when benzene is heated in air, it forms sooty flame, fine, and it produces carbon dioxide and water. So moving ahead, talking about the toxicity of benzene. So when organic molecules, compounds have more than 2 repeating units of benzene, fine. So benzene, that is more than 2 repeating units of benzene in the organic compound, which is formed by fusing benzene molecules together, fine. All these compounds are said to be toxic. That is, they have cancer-causing properties and they are formed on incomplete combustion of organic materials like tobacco, coal, or the petroleum, right? People say that tobacco is carcinogenic, right? It's harmful for health. This is the reason, because it is formed due to the incomplete combustion and which causes cancer. So what happens is they get into the human body and cause some biochemical reactions, and then they damage DNA and cause cancer. Hence, the organic compounds having repeating units of benzene, that is benzene fused together, are all toxic. And this is all about the aromatic hydrocarbons. Hello everybody. I hope you are liking this course, and if yes, hit the like button and share it among your friends. And please do subscribe to read my course and check out their other videos as well. There are a lot of interesting videos. And thank you for watching.